10 billion light-years. This is not the distance to some far-off galaxy. This is the size of a single object that astronomers discovered in 2013 and which has since haunted every cosmologist on the planet. A structure so monstrous in its scale that, by all known laws of physics, it simply should not exist. But it exists, and no one can explain exactly how it appeared. Imagine an object so huge that it takes light 10 billion years to cross it from end to end. For comparison, light crosses our Milky Way galaxy in about 100,000 years. This means that this structure is 100,000 times larger than our home galaxy. 100,000 times. Try to grasp these figures, and you will understand why scientists are still arguing about whether it is real at all or some incredible optical illusion of cosmic proportions. Tonight you will learn 3 things that will forever change your perception of the scale of the universe. First, exactly how astronomers accidentally stumbled upon this structure while studying a completely different phenomenon. Second, why the existence of this object contradicts the fundamental principle of cosmology on which our entire understanding of the universe is built. And third, what other mysterious giant structures are hidden in the depths of space, forming something like a skeleton or a web, the existence of which we did not even suspect 30 years ago. This is not just a story about one big object. It is a story about how science encountered something so inexplicable that some researchers seriously considered revising the basic laws of cosmology. You are learning something that might keep you awake, or, conversely, immerse you in reflections on infinity and our place in it. If you are fascinated by the secrets of space and riddles that even the most brilliant minds of humanity cannot solve, subscribe to the channel. The journey into the abyss begins right now. To understand why the discovery of this structure caused such a shock in the scientific community, we first need to understand how the universe is structured on large scales. More precisely, how we thought it was structured before this discovery. For almost 100 years, cosmology has relied on one fundamental principle called the cosmological principle. It sounds boring, but in fact, it is one of the most beautiful and simultaneously most controversial ideas in the history of science. Its essence is simple. If you look at the universe on sufficiently large scales, it should look the same in any direction and from any point. No special places, no privileged positions, no giant structures that would break this uniformity. This principle did not appear out of nowhere. It was a philosophical reaction to centuries of anthropocentrism, when people believed that the Earth was at the center of the universe, until Copernicus, and then Galileo, proved that we rotate around the sun. This was the first blow to human ego. Then it turned out that our sun is just one of hundreds of billions of stars in the Milky Way galaxy. Then it was revealed that the Milky Way is just one of hundreds of billions of galaxies in the universe, and the cosmological principle became the logical conclusion of this chain. We are not just not at the center, we are in an absolutely typical, unremarkable place in space. Albert Einstein put this principle at the basis of his general theory of relativity when applying it to cosmology. All models of the expanding universe, starting from the works of Alexander Friedman in the 20s of the 20th century, assume that matter is distributed in the universe more or less evenly. Yes, there are galaxies and clusters of galaxies. There are voids between them. But if you take a large enough volume of space, say several 100 million light-years, the density of matter should be roughly the same everywhere. This is not just an abstract idea. The cosmological principle lies at the core of our understanding of the Big Bang, the expansion of the universe, the formation of galaxies, cosmic microwave background radiation, practically everything we know about space. Without this principle, modern cosmology would simply fall apart. And this is where the most interesting part begins. Scientists have long known that the universe is not perfectly uniform. We see galaxies, clusters of galaxies, superclusters. There is the famous Sloan Great Wall, discovered in 2003, a giant structure of galaxies about 1.5 billion light-years long. There is an even larger Hercules Great Wall stretching about 600 million light-years. All these structures seemed large but still fit within the framework of the cosmological principle. It was believed that there is a certain limit after which inhomogeneities smooth out and the universe becomes truly uniform. This limit was estimated at about 300 to 400 million light-years, a maximum of 1 billion. Now imagine that you are an astronomer studying gamma-ray bursts, some of the most powerful explosions in the universe. Gamma-ray bursts occur when massive stars die or neutron stars collide. In fractions of a second, they release as much energy as our sun will release in its entire existence. It is thanks to this monstrous brightness that we can observe gamma-ray bursts at unimaginable distances in the farthest corners of the visible universe. In 2013, a group of Hungarian and American astronomers, led by István Horváth from the National University of Public Service in Budapest, studied the distribution of gamma-ray bursts across the sky. They used data accumulated over years of observations by various space observatories. The aim of the study was to check whether gamma-ray bursts are indeed distributed evenly in all directions, as predicted by the cosmological principle. What they found shocked them. In the constellations of Hercules and Corona Borealis, at a distance of about 10 billion light-years from Earth, an anomalous concentration of gamma-ray bursts was observed. Not just a small excess over the average level, but a statistically significant surplus. Gamma-ray bursts seem to cluster in a certain region of the sky, forming an arc-like structure. At first, scientists decided it was a statistical fluctuation, a random deviation that would disappear with more thorough analysis. But the more data they checked, the clearer it became. This was not a coincidence. The probability that such a distribution arose by chance was less than 1/10,000th. In science, this is considered practically ironclad proof of the reality of the phenomenon. The fact is that gamma-ray bursts are connected with galaxies. They occur where there are stars, and stars are where there are galaxies. If an excess of gamma-ray bursts is observed in a certain region of the sky at a certain distance, it means there is an excess of galaxies there. Many galaxies, very many galaxies. So many that they form a structure whose size exceeds 10 billion light-years. Thus, the Hercules Corona Borealis Great Wall was discovered, the largest known object in the universe, a structure that, by all known laws of physics, should not exist. To give you even a remote idea of these scales, let's make a few comparisons. The diameter of the Earth is about 12,700 kilometers. The distance from the Earth to the Moon is approximately 384,000 kilometers. The distance from the Earth to the Sun is about 150 million kilometers, or 1 astronomical unit. Light covers this distance in about 8 minutes. Now let's move to stellar scales. The nearest star to us after the Sun, Proxima Centauri, is at a distance of about 4 2/10 light-years. This means that light from it takes more than 4 years to reach us. Our galaxy, the Milky Way, has a diameter of about 100,000 light-years and contains from 200 to 400 billion stars. The nearest large galaxy, Andromeda, is at a distance of about 2.5 million light-years. The local group of galaxies, which includes the Milky Way, Andromeda, and dozens of other smaller galaxies, has a diameter of about 10 million light-years. The Laniakea supercluster, of which our local group is a part, stretches for about 520 million light-years and contains about 100,000 galaxies. And now back to the Hercules Corona Borealis Great Wall. Its size is more than 10 billion light-years. This is 20 times larger than the Laniakea supercluster. This constitutes about 1/10 of the diameter of the entire observable universe. One object occupies 10% of everything we can fundamentally see. Official science recognized the discovery quite quickly, but disputes about its interpretation immediately began. Some astronomers suggested that this is not a single structure, but a random superposition of several smaller structures that are simply at about the same distance from us. Others pointed to the limited data on gamma-ray bursts. Relatively few have been registered, and the statistics might be unreliable. Still others questioned the methodology of the study altogether. However, subsequent years only strengthened the initial conclusions. Additional data confirmed the existence of the anomaly. Moreover, other giant structures were discovered that also challenged the cosmological principle. In 2021, British astronomers from the University of Central Lancashire announced the discovery of the so-called Giant Arc, a structure about 3,300,000,000 light-years long, located at a distance of about 9 billion light-years from Earth. In the same year, another anomaly was discovered, the Big Ring, a structure with a diameter of about 1,300,000,000 light-years. Interestingly, the Giant Arc and the Big Ring are in the same region of the sky, which suggests the existence of an even larger scale structure of which they are parts. And this structure might rival the size of the Hercules Corona Borealis Great Wall itself. All this poses an uncomfortable question for scientists. What if the cosmological principle is incorrect? What if the universe on large scales is not uniform and isotropic at all? What if there are structures that stretch across a significant part of the observable universe? The consequences of such a conclusion would be catastrophic for modern cosmology. We would have to revise the Big Bang models, inflation theory, calculations of the age of the universe, and the understanding of dark matter and dark energy. Practically everything. But there is another possibility, even more intriguing. What if these structures indeed exist, but their appearance can be explained by some processes unknown to us that do not contradict the cosmological principle, but complement it? What if we simply do not understand exactly how large-scale structures were formed in the universe? Some theorists suggest that giant structures could have formed even before the universe became transparent to light, in the first hundreds of thousands of years after the Big Bang. In those times, quantum fluctuations could have created abnormally large inhomogeneities in the distribution of matter, which then grew to the scales observed today. Others point to the role of dark matter. We know that dark matter makes up about 27% of the mass energy of the universe, but we know practically nothing about its properties. Perhaps dark matter is capable of forming structures that ordinary matter simply cannot create because of its interaction with radiation. There is another hypothesis, the most radical one. What if what we see are not separate structures, but the manifestation of some global pattern permeating the entire universe? What if the universe has some hidden topology, a kind of cosmic crystalline lattice, the nodes of which are these giant walls and filaments? This idea might seem like science fiction, but it has a certain theoretical basis. Back in the 60s, Soviet physicist Yakov Zeldovich developed a theory according to which matter in the universe should gather into flat structures, so-called Zeldovich pancakes. These pancakes then intersect, forming filaments and nodes. The entire universe, according to this theory, represents a giant three-dimensional web, the threads of which consist of galaxies. And the voids between the threads are occupied by huge cosmic voids. Modern computer simulations confirm this picture. When scientists model the evolution of the universe from the Big Bang to the present day, they get exactly such a mesh structure. But the sizes of the observed giant walls still go beyond what the simulations predict. Perhaps the problem is in the simulations themselves. They are based on certain assumptions about initial conditions and the laws of physics. And these assumptions might be incorrect, or they simply do not take into account some factors that we do not yet understand. Or maybe the problem is in our observations. Gamma-ray bursts are not an ideal tool for mapping large-scale structures. Too few are registered, and linking them to specific distances is not always reliable. Perhaps when we have more accurate data, the Hercules Corona Borealis Great Wall will turn out to be an illusion created by the limitations of our observation methods. But reality turns out to be much more disturbing. Every year we find more and more evidence that giant structures are real and that their existence calls into question our understanding of the very fabric of space-time. In 2015, a group of astronomers announced the discovery of the so-called Eridanus supervoid, a giant void in space whose diameter is about 1,800,000,000 light-years. Inside this void, there are practically no galaxies, only rarefied gas, and presumably dark matter in minimal concentrations. The Eridanus supervoid is linked to the so-called cold spot in the cosmic microwave background, an abnormally cold area on the map of the cosmic microwave background observed in the same direction of the sky. If the Hercules Corona Borealis Great Wall is an anomalous accumulation of matter, then the Eridanus supervoid is an anomalous absence of matter. Both these anomalies violate the cosmological principle just in opposite directions. And that's not all. There is a mystery known as the axis of evil, a strange correlation in the patterns of the cosmic microwave background radiation that points to the existence of a certain preferred direction in the universe. If the universe is isotropic, there should be no such direction. But it exists, and it points roughly to where some of the giant structures are located. Is it possible that all these anomalies are interconnected? Is it possible that we are observing the manifestation of some single phenomenon that does not yet fit into our theoretical frameworks? Some researchers go even further and suggest that our universe might be part of a multiverse, an infinite multitude of universes with different physical laws. Giant structures, in their opinion, could be traces of collisions of our universe with neighboring universes in the distant past. These collisions left scars on the fabric of our space-time, which we observe today as anomalous clusters or voids. This is, of course, a very speculative hypothesis that cannot be verified with current methods. But the very fact that serious scientists consider such exotic explanations speaks to the depth of the problem. We have indeed encountered something that does not fit into the usual frameworks. The official position of most cosmologists remains cautious. They recognize the existence of anomalies, but point to the insufficiency of data for final conclusions. The cosmological principle, in their view, remains in force. Simply, the scale of uniformity turned out to be larger than we assumed. The universe is uniform not on scales of hundreds of millions of light-years, but on scales of tens of billions. This is unpleasant for the theory, but not fatal. However, even this position raises questions. If the scale of uniformity is comparable to the size of the observable universe, then how can we even check the cosmological principle? We see only one universe, and we see it only from one point. If the inhomogeneities are comparable in size to what we can observe, the principle becomes unfalsifiable and therefore unscientific. This leads us to a philosophical question about the limits of scientific knowledge. Perhaps there are things we simply cannot know, not because of technical limitations, but because of the very nature of reality. We are locked inside the observable universe, and everything outside its borders will forever remain inaccessible to us. But reality turns out to be even stranger and more frightening than this measured philosophizing. Because giant structures are not just clusters of galaxies peacefully floating in the void. They are arenas of monstrous cataclysms whose energy is enough to destroy all life within a radius of millions of light-years. When we talk about the large-scale structures of the universe, we inevitably encounter a question that seems simple, but in reality hides one of the deepest mysteries of modern physics. How did anything arise from nothing? How did galaxies, clusters of galaxies, and those monstrous megastructures we talked about appear from the initial uniform soup of the early universe? To approach the answer, we will have to take a journey to the very beginning of time. Approximately 13,800,000,000 years ago, all matter and energy that today make up the observable universe were compressed into an unimaginably small volume. The density and temperature were so high that the laws of physics known to us simply did not work. This state is called a singularity, although it would be more honest to say that we do not have the slightest idea what it actually was. Then the Big Bang occurred, but it was not an explosion in the usual sense. There was no center from which matter flew in different directions. Space itself began to expand, carrying matter and energy with it. And in the first fractions of a second of this expansion, something critically important for our story happened. According to modern cosmological theory, in the period between 10 to the minus 36th and 10 to the minus 32nd seconds after the start of the Big Bang, the universe experienced a phase of so-called inflation. In this unimaginably short time, space expanded a colossal number of times. According to some estimates, the volume of the universe increased by 10 to the 78th power times. This is as if an atom suddenly expanded to the size of the observable universe, and even this comparison does not convey the true scale. Inflation explains why the universe today looks so uniform on large scales. Any inhomogeneities that existed before inflation were stretched to incredible sizes and smeared across space. The universe became smooth like the surface of a balloon being inflated harder and harder. But here is the paradox. If inflation made the universe so uniform, then where did galaxies come from? Where did stars and planets come from? You and I? Where did that giant structure that should not exist come from? The answer lies in quantum mechanics. On the smallest scales, the world obeys not the logic familiar to us, but the probabilistic laws of quantum physics. One consequence of these laws is the so-called quantum fluctuations. Even in an absolute vacuum, pairs of virtual particles constantly appear and disappear. Space literally boils with these fleeting disturbances. During inflation, quantum fluctuations were stretched together with space. What was a microscopic disturbance became a macroscopic inhomogeneity. Where a fluctuation created a slightly higher density of matter, gravity began to attract even more matter. Where the density was slightly less, matter flowed into neighboring regions. Thus, microscopic quantum oscillations became the seeds of future galaxies and all large-scale structures. This process took hundreds of millions of years. In the first roughly 380,000 years after the Big Bang, the universe was filled with hot plasma, opaque to light. Photons were constantly scattered by free electrons and could not travel any significant distance. Gravity was already working, attracting dark matter to zones of increased density, but ordinary matter was too hot to follow it. Then the universe cooled enough for electrons to start combining with protons, forming neutral hydrogen atoms. This era is called recombination. The universe suddenly became transparent. The light that was locked in the plasma broke free and began its journey through expanding space. It is this light that we observe today as cosmic microwave background radiation, the oldest light in the universe, carrying information about its state 380,000 years after birth. Maps of this radiation, compiled by space observatories, show those very primary inhomogeneities. Tiny differences in temperature of the order of 100,000th of a degree reflect differences in matter density at the moment of recombination. Hotter spots correspond to regions with slightly lower density, colder regions to regions with slightly higher density. This is literally a photograph of the embryos of all future structures of the universe. But the scale of these primary inhomogeneities is limited. Inflation theory predicts that fluctuations should have a certain spectrum, a distribution by size. Large fluctuations should be weaker than small ones. This means that very large structures should form later and be less pronounced. And here is where the problems begin. According to standard calculations, the maximum size of a structure that could have formed during the existence of the universe under the action of gravity is approximately 300 to 500 million light-years. This is the so-called limit of uniformity, or the scale of homogeneity. Above this limit, inhomogeneities should smooth out, and the universe should become statistically uniform. But we observe structures whose size exceeds this limit dozens of times. The Hercules Corona Borealis Great Wall has a size of more than 10 billion light-years. This means that either our calculations are wrong or these structures formed in some other way that we do not yet understand. Let's look closer at the mechanism of the formation of large-scale structures. After recombination, gravity began to gather matter into clumps, but the process was uneven. Dark matter, which does not interact with electromagnetic radiation, began to collapse first. It formed so-called halo-spherical clouds, inside which galaxies of ordinary matter later appeared. Dark matter halos did not exist in isolation. They were connected to each other by filaments, thin bridges of dark matter connecting neighboring clumps. Where several filaments intersected, nodes of increased density were formed. Gradually, the entire universe acquired the structure of a giant three-dimensional network, which astronomers call the cosmic web. The cosmic web is the frame of the universe. All galaxies, including our Milky Way, are located along the threads of this web or in its nodes. Between the threads lie voids, huge emptinesses, practically devoid of matter. The diameter of a typical void is from 100 to 300 million light-years. In the voids, it's not like there is absolutely nothing, but the density of matter there is dozens and hundreds of times lower than the average in the universe. If you look at the map of galaxy distribution compiled from modern sky surveys, such as the Sloan Digital Sky Survey, the picture of the cosmic web becomes obvious. Galaxies are not distributed randomly. They form a complex hierarchical structure of filaments, walls, and nodes, interspersed with voids. Walls are particularly interesting formations. These are flat or slightly curved surfaces consisting of many galaxies located in a relatively thin layer. All known Great Walls belong to this type of structure: the Sloan Great Wall, the Hercules Great Wall, and others. The formation of walls occurs as follows. Under the action of gravity, matter collapses anisotropically, not the same in different directions. First, collapse occurs along one direction, and matter flattens into a plane. Then collapse begins along a second direction, and the plane is pulled into a thread. Finally, collapse along a third direction creates compact clumps, nodes from which galaxy clusters are formed. This process is mathematically described by the so-called pancake model mentioned earlier. The first structures to form are precisely flat formations, like pancakes. Filaments and nodes arise later, when these pancakes start to collide and intersect with each other. Modern supercomputers allow for modeling this process with incredible detail. Simulations like Illustris or Millennium use billions of particles to track the evolution of matter throughout the history of the universe. The results of these simulations reproduce the observed picture of the cosmic web surprisingly well: filaments, walls, nodes, voids. But here's the catch. Even the most large-scale simulations, covering cubic volumes of space several billion light-years in size, do not produce structures comparable in size to the Hercules Corona Borealis Great Wall. Simulations give walls and filaments with a size of at most several hundred million light-years, roughly what the theory predicts. No, nay, 10 billion. This is a serious problem. If our simulations are correct, then such a structure should not exist. If it exists, it means the simulations are missing something. Perhaps the initial conditions we use do not correspond to the real ones. Perhaps dark matter behaves differently than we assume. Perhaps there are some additional forces or processes that we have not included in our models. One hypothesis is linked to the so-called dark energy, the mysterious force responsible for the accelerated expansion of the universe. Dark energy makes up about 68% of all energy in the universe, but we know practically nothing about it. Its properties are described by the cosmological constant, a number that Einstein once introduced into his equations, then rejected, and modern cosmology was forced to bring back. If dark energy is unevenly distributed across the universe, this could explain the existence of abnormally large structures. In regions where there is less dark energy, gravity acts more effectively, and matter gathers into larger clusters. In regions where there is more dark energy, expansion is accelerated and giant voids are formed. The problem is that the Standard Model assumes that dark energy is absolutely uniform. It has the same density at every point in space and does not change over time. If this is not the case, we will have to completely revise our understanding of cosmology. Another hypothesis is linked to primary inhomogeneities. What if quantum fluctuations during inflation were not as random as we think? What if there were special regions with abnormally large fluctuations that later grew into giant structures? Inflation theory allows for such a possibility. If the inflationary field, the scalar field responsible for inflation, had an uneven distribution, this could have created primary inhomogeneities of a non-standard spectrum. Regions with stronger fluctuations would become the embryos of ultra-large structures. No, it is very difficult to verify this hypothesis. We can only observe the imprint of primary fluctuations on the cosmic microwave background radiation, and the resolution of these observations is limited. Furthermore, we see only one universe. If giant structures are the result of rare statistical deviations, we simply have no opportunity to check how rare they actually are. Another intriguing idea is linked to the topology of space. Einstein's general theory of relativity describes how matter and energy curve space-time, but it says nothing about the global shape of the universe. The universe could be infinite and flat, like an infinite sheet of paper, or it could be finite but without borders, like the surface of a sphere. Or it could have a more complex topology, for example, be like a torus, a donut. If the universe has a non-trivial topology, we could see the same structures from different directions. Light from a distant galaxy could go around the universe and reach us from the opposite side of the sky. This could create the illusion of structures that are actually repeating images of the same objects. Cosmologists searched for signs of such topology in the cosmic microwave background data, but have not yet found convincing evidence. This does not mean that non-trivial topology is impossible. Simply, the scale of the universe might be larger than the observable horizon, and we do not see repetitions. There is another factor that must be considered when analyzing giant structures: their age. The Hercules Corona Borealis Great Wall is located at a distance of about 10 billion light-years from us. This means that light from it has been traveling to us for 10 billion years. We see this structure as it was 10 billion years ago, when the universe was less than 4 billion years old. This is a very early era. The universe was younger, denser, hotter. Structures were just forming. What we see as a great wall could have been just the embryo of a future structure, a region with increased matter density that had not yet had time to completely collapse. No, even accounting for this, the problem remains. To create an inhomogeneity 10 billion light-years in size in 4 billion years requires an incredibly large initial disturbance, so large that standard theory does not predict it. Mathematically, the situation is as follows. The speed of propagation of gravitational disturbances is limited by the speed of light. In 4 billion years, gravitational influence can spread to a maximum of 4 billion light-years. A structure larger than that simply would not have had time to form. Its parts would not have been able to learn about each other. This is the so-called causality horizon, and it imposes strict limits on the size of structures that could have arisen after the Big Bang. Structures larger than the causality horizon must have existed initially, even before gravitational evolution began. No, this means they somehow survived inflation, which was supposed to smooth out all inhomogeneities. Is it possible that some inhomogeneities were so massive that even inflation could not completely eliminate them. This sounds exotic, but some theoretical models allow for such a possibility. If inflation was not ideal, if it occurred slightly differently in different regions, this could have created large-scale anomalies. There are even more radical ideas. Some physicists suggest that our universe is not the only one. According to the theory of eternal inflation, the Big Bang that gave birth to our universe was only one of an infinite number of such events. Universes are continuously born from quantum fluctuations in the inflationary field, like bubbles in boiling water. If this is so, our universe might border other universes, and these borders or traces of past collisions could manifest as anomalies in the distribution of matter. Giant structures and voids could be scars from encounters between our universe and its neighbors. This is, of course, a very speculative hypothesis. We have no direct evidence of the existence of other universes, and it is unknown whether such evidence can in principle be obtained. But the very fact that scientists consider such ideas shows how serious the challenge posed by giant structures is. Let's look at the problem from another angle. Perhaps it's not that we don't understand something in physics, but that we are incorrectly interpreting the observations. The Hercules Corona Borealis Great Wall was discovered using gamma-ray burst data, but gamma-ray bursts are not a simple object for analysis. Only a few hundred gamma-ray bursts are registered each year. Their distribution across the sky is uneven. We see those that occurred far from the plane of our galaxy better, where there is less gas and dust. Determining the distance to a gamma-ray burst is also not easy. It is based on measuring the redshift, which cannot always be obtained accurately. If there are systematic errors or biases in the data, this could create a false impression of the existence of a structure. Imagine that you are looking at the sky through dirty glass with uneven spots. Stars behind the spots will be seen worse, and it might seem that there are fewer of them there. But this will be an illusion created by your observation tool, not a real inhomogeneity. Critics of the discovery point to several potential sources of such errors. First, the sample of gamma-ray bursts is relatively small. Only a few thousand objects over a decade of observations. With such a sample, statistical fluctuations can be significant. Second, different space observatories have different sensitivities and different viewing zones, which creates uneven sky coverage. Third, methods for determining the distance to gamma-ray bursts are constantly improving, and old data might contain systematic errors. However, the authors of the discovery performed a thorough analysis of all these effects and concluded that they cannot explain the observed anomaly. The probability of the accidental emergence of such a structure remains very low, less than 1% by the most conservative estimates. Furthermore, the existence of giant structures is confirmed by independent observations. The previously mentioned giant arc and big ring were discovered using completely different methods, by the distribution of quasars, not gamma-ray bursts. Quasars are the active nuclei of galaxies, at the center of which are supermassive black holes consuming surrounding matter. They shine so brightly that they are visible at huge distances, and there are hundreds of thousands of them in catalogs. If different observation methods give consistent results, this strengthens confidence in the reality of giant structures. Random errors in different methods should not create identical artifacts. There is another argument in favor of the reality of these structures: their connection with other cosmological anomalies. The cold spot in the cosmic microwave background radiation, located in the constellation Eridanus, almost perfectly coincides with the position of the Eridanus supervoid. This cannot be a random coincidence. The light of the cosmic microwave background, passing through the void, loses energy because of the expansion of space inside the void, which creates the cold spot. If voids and cold spots are connected, it is logical to assume that superclusters are connected with hot spots of the cosmic microwave background. And indeed, statistical analysis shows a correlation between the distribution of galaxies and the anisotropy of the cosmic microwave background. All this points to the fact that the large-scale structure of the universe is real and has a deep connection with the initial conditions of the Big Bang. But the exact mechanism of the formation of giant structures remains unknown. Modern cosmology is in a strange position. On one hand, we have the Standard Model, the so-called lambda CDM, which describes a universe consisting of ordinary matter, cold dark matter, and dark energy in the form of a cosmological constant. This model is incredibly successful. It explains the expansion of the universe, the cosmic microwave background radiation, the formation of galaxies, the synthesis of light elements after the Big Bang, and many other observations. On the other hand, the model faces a number of anomalies that do not fit into its framework. Giant structures are just one of them. There is also the Hubble constant problem. Different methods of measuring it give different values, and this discrepancy cannot be explained by statistical errors. There is the problem of small galaxies. Simulations predict far more dwarf galaxies around large ones than we observe. There is the problem of the satellite plane. The satellite galaxies of the Milky Way are located in a thin plane, which is difficult to explain by chance. Each of these anomalies individually might have an innocent explanation: systematic errors in observations, uncounted physical effects, statistical fluctuations, but together they form a disturbing picture. Perhaps the Standard Model, for all its success, misses something fundamental. Some physicists suggest that the answer lies in the modification of gravity. Einstein's general theory of relativity, on which standard cosmology is based, works perfectly in the solar system and even on the scales of galaxies. No, on cosmological scales of billions of light-years, it has never been tested directly. What if gravity behaves differently at very large distances? There are theories of modified gravity, such as Mond or FR theory, which offer an alternative to dark matter and dark energy. In some of these theories, gravity is strengthened on large scales, which could explain the formation of giant structures without resorting to exotic physics. No, modified gravity theories face their own problems. It is difficult for them to explain the entire variety of observational data that the Standard Model describes so successfully. Replacing one theory with another creates almost as many new questions as it solves old ones. In the final analysis, the honest answer is this: we do not know how to explain the existence of giant structures. Standard cosmology predicts an upper limit for the size of structures, and this limit is violated. Either our observations are wrong, or our theory is incomplete. Science usually develops precisely like this, through the collision of theory with observations that contradict it. Giant structures might turn out to be that very key that opens the door to a new understanding of the universe, or they might turn out to be a statistical illusion that disappears with more thorough data analysis. No, even if the structure turns out to be real, its existence poses a question deeper than just a physical mechanism of formation. This is a question about humanity's place in the universe, which turns out to be much stranger and more unpredictable than we thought. A universe in which forces and processes act whose scale surpasses our imagination. To truly grasp the scale of giant cosmic structures, we need to take a journey through the most impressive of them, consider their internal arrangement, and understand what processes occur in these colossal formations. Each of these structures is not just a cluster of galaxies, but a complex system where gravity, matter, and energy interact on scales that are difficult to fit into human consciousness. Let's start with our cosmic address. Earth is in the solar system. The solar system is in the Milky Way galaxy. The Milky Way is in the local group of galaxies. The local group is in the Laniakea supercluster. The name Laniakea itself comes from Hawaiian words meaning immense heavens, and this name is more than justified. Laniakea was defined as a single structure only in 2014 by a team of astronomers led by Brent Tully from the University of Hawaii. Before that, it was believed that we belonged to the Virgo supercluster, a much smaller structure with a diameter of about 110 million light-years. No new analysis methods showed that the Virgo supercluster is only a small part of a much more extensive formation. Laniakea stretches for about 520 million light-years and contains about 100,000 galaxies with a total mass of the order of 100 quadrillion solar masses. This is a number with 17 zeros. Now, what makes Laniakea a single structure and not just a random cluster of galaxies? The answer lies in gravitational flows. All galaxies inside Laniakea move in a certain direction, attracted by a common center of masses. This center is called the Great Attractor, a mysterious region that is itself one of the greatest mysteries of cosmography. The Great Attractor was discovered back in the 70s of the 20th century. When astronomers noticed that our galaxy and its neighbors were not just moving by the inertia of the expansion of the universe, but had an additional speed of about 600 kilometers per second in the direction of the constellations Centaurus and Norma. Something huge was attracting us to it. The problem is that the Great Attractor is located behind the plane of our own galaxy in the so-called zone of avoidance, where the gas and dust of the Milky Way block the view. We literally cannot see what is there in the optical range. Only observations in the X-ray and infrared ranges allowed for partially lifting the veil. It turned out that in the direction of the Great Attractor is the massive Norma cluster of galaxies, also known as Abell 3627. This cluster contains thousands of galaxies and is one of the most massive in the local universe. No, even its mass is insufficient to explain the observed attraction. Further research showed that behind the Norma cluster hides an even more grandiose structure, the Shapley supercluster, named after astronomer Harlow Shapley. This is one of the densest accumulations of matter in the observable universe, containing more than 20 individual clusters of galaxies. It is the combined attraction of all these masses that creates that gravitational flow we call the Great Attractor. No, the story does not end there. In 2017, another structure was discovered located behind the Shapley supercluster, the so-called dipole repeller. Unlike the Great Attractor, this region is characterized by an abnormally low density of matter. This is a cosmic void that sort of repels surrounding galaxies from itself. An interesting picture emerges. We are simultaneously being pulled toward the Great Attractor and pushed away from the dipole repeller. Both effects add up, creating the observed movement of our galaxy in space. We are flying through space at a speed of more than 600 kilometers per second, carried by gravitational tides of structures that we cannot even clearly see. Now imagine that all of Laniakea, with all its 100,000 galaxies, the Great Attractor, the Shapley supercluster, is just a tiny fragment of those giant structures we are talking about. The Hercules Corona Borealis Great Wall is 20 times larger than Laniakea. It contains not 100,000, but millions or even tens of millions of galaxies. Let's look at other known Great Walls to better understand their nature. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, has a length of about 1.5 billion light-years. It is located at a distance of approximately 1 billion light-years from Earth and contains several large superclusters of galaxies. The structure of the Sloan Great Wall resembles a curved ribbon or a wave stretching through space. Its thickness is relatively small, only a few tens of millions of light-years, which makes it look like a giant cosmic sheet. Galaxies inside the wall are not distributed evenly. They cluster into filaments and nodes, forming a complex internal structure. Another impressive structure is the CFA-2 Great Wall, also known as the Hukra-Geller Great Wall in honor of its discoverers. It was found in 1989 and became the first Great Wall recognized by the scientific community. Its length is about 750 million light-years, and the distance to us is approximately 200 million light-years. The discovery of the CFA-2 Great Wall produced a revolution in our understanding of the large-scale structure of the universe. Before that, astronomers imagined the distribution of galaxies as more or less random with small clusters here and there. The discovery of a giant connected structure showed that the universe is organized much more hierarchically than assumed. After this discovery, many others followed. The Boss Great Wall, discovered in 2016, stretches for 1 billion light-years. The South Pole Wall, found in 2020, has a length of about 1.5 billion light-years and is notable for being relatively close to us, only 500 million light-years away. Every new discovery expanded the boundaries of known structures. It seemed that every time we build a more detailed map of the universe, we find even larger formations. And the culmination of this process was the discovery of the Hercules Corona Borealis Great Wall, a structure so huge that it calls into question the very foundations of cosmology. Inside these giant structures, processes of colossal scale occur. Galaxies do not just hang in the void, they move, interact, and collide with each other. And these collisions generate phenomena of such power that it is difficult to imagine. Take a typical collision of two large galaxies. When a galaxy the size of the Milky Way meets a galaxy the size of Andromeda, and this will happen in about 4.5 billion years, the result will be catastrophic by cosmic standards. Gravitational forces deform both galaxies, pulling out long tidal tails of stars and gas. The spiral structure is destroyed. Gas clouds collide at speeds of hundreds of kilometers per second, generating shock waves and starbursts. Interestingly, the stars themselves in such collisions practically do not collide with each other. The distances between stars inside a galaxy are so enormous compared to the sizes of the stars themselves that the probability of a direct collision is negligibly small. If the Sun is reduced to the size of a grain of sand, the nearest star would be at a distance of several kilometers. Two galaxies pass through each other like two swarms of bees. No gas is another matter. Interstellar gas fills the space between stars. And when two gas clouds collide at high speed, the collision energy is converted into heat. The gas heats up to millions of degrees and starts to radiate in the X-ray range. Simultaneously, the compression of gas triggers processes for forming new stars, sometimes in such quantities that the galaxy is called a starburst galaxy. Supermassive black holes at the centers of both galaxies also interact. First, they rotate around each other at a distance of thousands of light-years, gradually closing in. This process takes hundreds of millions of years. Ultimately, the black holes merge, releasing a monstrous amount of energy in the form of gravitational waves. Gravitational waves from the merger of supermassive black holes are one of the most powerful phenomena in the universe. When two black holes with a mass of billions of suns merge, they release, in fractions of a second, energy equivalent to the total conversion of several solar masses into energy. This is more than all the energy emitted by all the stars in all the galaxies of the observable universe in the same period of time. In giant structures like great walls, such mergers occur regularly. Not every day, of course, but over billions of years, thousands of galaxies collide and merge. Their black holes combine, and gravitational waves spread in all directions, making space itself vibrate. We only started registering gravitational waves in 2015, thanks to LIGO detectors. So far, we have fixed only the mergers of relatively small black holes, stellar masses with masses in the dozens of suns. To register mergers of supermassive black holes, detectors of a completely different type are needed, so-called pulsar timing arrays, which use pulsars as giant cosmic clocks. In 2023, several independent groups announced the discovery of the so-called gravitational wave background, a low-frequency hum of gravitational waves permeating the entire universe. This background is likely created by many merging supermassive black holes across the cosmos. We are literally hearing the echo of catastrophes occurring in distant galaxies. No, the merger of galaxies is not the only source of energy in the Great Walls. When galaxies fall into the gravitational pit of a cluster, they accelerate to huge speeds, sometimes several thousand kilometers per second. Gas falling together with the galaxies experiences so-called ram pressure stripping. The hot gas of the cluster acts like a headwind, stripping the cold gas from the falling galaxy. This process is clearly visible in images of galaxy clusters. Galaxies falling toward the center of a cluster often have characteristic tails of gas stretched in the direction opposite to the direction of motion. This is like a smoke trail behind a flying plane, only the scale is completely different. Tails can stretch for hundreds of thousands of light years. Stripped of gas, the galaxy can no longer form new stars. Old stars continue to shine, but new ones are not born. Gradually, the galaxy ages and fades, turning into a so-called red and dead elliptical galaxy. This is exactly why elliptical galaxies predominate in the centers of rich clusters. Spiral galaxies falling there quickly lose their gas and transform. The cluster gas itself is another story. It is invisible to ordinary telescopes because it is too hot to radiate in the optical range. The temperature of this gas reaches 100 million degrees. This is 10 times hotter than the core of the sun. At this temperature, the gas radiates in the X-ray range, and X-ray telescopes like Chandra or XMM Newton show galaxy clusters as bright glowing clouds. This red-hot gas contains more mass than all the stars in all the galaxies of the cluster combined. A typical rich cluster can contain about 100 trillion solar masses of hot gas. This gas is in a state of hydrostatic equilibrium. Its pressure balances the gravitational attraction of the cluster, preventing it from collapsing. No, the equilibrium is unstable. Gas constantly loses energy through radiation and should cool and fall toward the center of the cluster. However, observations show that this does not happen. Central regions of clusters are not flooded with cold gas. Something heats the gas, maintaining it in a hot state. The main candidate for the role of heating source is active galactic nuclei. At the center of almost every rich cluster is a giant elliptical galaxy, in whose core sits a supermassive black hole. This black hole periodically awakens when enough gas falls into it. The accretion process releases enormous energy, which is ejected in the form of relativistic jets, narrow beams of plasma moving at almost the speed of light. Jets pierce the surrounding gas, creating giant bubbles or cavities in it. These bubbles are clearly visible on X-ray images as dark areas inside the bright gas cloud. The sizes of the bubbles can reach hundreds of thousands of light years, larger than the diameter of a typical galaxy. The energy contained in one such bubble is equivalent to the explosion of billions of supernovae. Bubbles expand, pushing gas outward and heating it through shock waves and turbulence. This prevents the gas from cooling and falling onto the central galaxy. A kind of thermostat arises. When the gas starts to cool, it falls onto the black hole, activating jets that heat the gas and stop the cooling. When the heating stops, the cycle starts again. This process, called active galactic nucleus feedback, plays a key role in the evolution of clusters and superclusters. Without it, central galaxies would continuously grow, absorbing cooling gas and turning into monsters of unimaginable proportions. Feedback regulates galaxy growth, maintaining a kind of balance. On the scale of great walls, these processes happen everywhere. Thousands of clusters, tens of thousands of active nuclei, countless jets and bubbles. The entire structure is permeated with energy flows that redistribute matter and heat the gas. This is not a static cluster of galaxies. It is a dynamic system pulsing with activity. No, the most impressive energy ejections occur not in clusters, but in individual galaxies, specifically in their nuclei. These are quasars, active galactic nuclei so bright that they outshine their host galaxy hundreds of times. A quasar is a supermassive black hole in the process of actively consuming matter. Gas falling onto the black hole forms an accretion disk around it. a flat spiral structure in which matter gradually sinks closer and closer to the event horizon. Friction between the layers of the disk heats the gas to millions of degrees, making it shine brightly across all ranges of the electromagnetic spectrum. The most powerful quasars radiate energy equivalent to 1 trillion suns. One quasar shines brighter than hundreds of billions of stars of the Milky Way combined, and this energy is released from a region no larger than the solar system. Quasars were particularly common in the early universe, at those distances and in those eras where we observe the Hercules Corona Borealis Great Wall. 10 billion years ago, when the universe was young, galaxy collisions occurred more often, and gas flows to central black holes were more abundant. The era of quasars, as this period is sometimes called, was a time of unprecedented activity and energy ejections. The great walls of that era were literally dotted with quasars. Each of them ejected a colossal amount of energy into space, ionizing the surrounding gas and influencing the formation of neighboring galaxies. Quasar radiation could stop star formation in galaxies at a distance of millions of light-years, evaporating their gas reserves. Besides radiation, quasars produced powerful winds, flows of ionized gas moving at speeds of thousands of kilometers per second. These winds swept gas out of the galaxy, stripping it of material for forming new stars. Some models suggest that it was quasar winds that were responsible for the most massive galaxies ceasing to form stars and turning into red elliptical giants. Imagine this whole picture. A giant structure 10 billion light-years in size containing millions of galaxies. In each galaxy, hundreds of billions of stars living their lives, being born and dying. Galaxies collide with each other, generating starbursts and black hole mergers. Galaxy clusters are filled with gas at a temperature of 100 million degrees. Quasars eject jets and winds reshaping the surrounding space. Gravitational waves spread in all directions, making the very fabric of space-time tremble. And all this is at such a distance that light from these events traveled to us for 10 billion years. We see only an ancient photograph, an imprint of long-past cataclysms. What is happening there now? If the word now makes sense at such distances at all, we will learn only in 10 billion years when light from these events finally reaches Earth. However, by that time, Earth will no longer exist. Our sun will have long gone out. Yet energetic processes in the Great Walls are not the only thing that makes them dangerous. The very geometry of these structures creates conditions for phenomena that can threaten the existence of life at cosmic distances. One of these phenomena is gamma-ray bursts, the very ones through which the Hercules Corona Borealis Great Wall was discovered. Gamma-ray bursts are short flashes of gamma radiation, the most rigid and energetic type of electromagnetic radiation. In a few seconds or minutes, a gamma-ray burst releases as much energy as the sun will release in its entire existence. Gamma-ray bursts are of two types, short and long. Short ones last less than 2 seconds and arise during the merger of neutron stars. Long ones continue from several seconds to several minutes and are linked to the collapse of massive stars, so-called hypernovae. When the core of a massive star collapses into a black hole, the outer layers of the star fall inward and are partially ejected back in the form of 2 narrow relativistic jets directed along the axis of rotation. Matter in these jets moves at a speed of more than 99% of the speed of light. The collision of fast-moving matter with slower matter generates shock waves in which gamma radiation is generated. If the jet is directed toward us, we see a bright gamma-ray burst. If the jet is directed in another direction, we see practically nothing. This explains why there are not many gamma-ray bursts. We only observe those whose jets accidentally point to Earth. In giant structures like Great Walls, gamma-ray bursts occur regularly. High galaxy density means a high star formation rate and therefore a high death rate for massive stars. Those clusters of gamma-ray bursts that allowed for the discovery of the Hercules Corona Borealis Great Wall reflect precisely this increased activity. If a gamma-ray burst occurred close enough to us, say, within a few thousand light years, the consequences would be catastrophic. Intense gamma radiation would destroy Earth's ozone layer, exposing the planet's surface to the lethal impact of solar ultraviolet radiation. Furthermore, gamma rays would cause chemical reactions in the atmosphere, producing toxic nitrogen oxide and causing acid rain. Some researchers suggest that one or several mass extinctions in Earth's history could have been caused by close gamma-ray bursts. The Ordovician-Silurian extinction, which occurred about 445 million years ago and destroyed about 85% of marine species, is sometimes linked to such an event. There is no direct proof, but indirect signs, for example, selective extinction of organisms in shallow zones, consistent with this hypothesis. In the context of great walls, this acquires special significance. If our galaxy ever finds itself inside such a structure, and we are already on the periphery of Laniakea, the probability of a close gamma-ray burst will significantly increase. The concentration of stars and galaxies in the Great Walls means a concentration of dangerous events, but gamma-ray bursts are not the only threat. Supernovae, galaxy collisions, active nuclei. All these phenomena can influence the habitability of planets within a radius of hundreds and thousands of light years. Cosmic radiation from these events can penetrate deep into the atmosphere and even reach the planet's surface, damaging DNA and disrupting biological processes. There is the concept of the so-called galactic habitable zone, a region inside a galaxy where conditions are favorable for life. This zone is at a certain distance from the galactic center, not too close where the star density is high and cataclysms are frequent, and not too far where there are few heavy elements necessary for forming Earth-type planets. By analogy, one can speak of a cosmic habitable zone, regions of the large-scale structure of the universe where life has the best chances to arise and persist. Voids with their low galaxy density and rare cataclysms could be more favorable for life than the Great Walls with their stormy activity. We are not at the center of a Great Wall, but also not deep in a void. Our local group is located on the periphery of the Laniakea supercluster in a relatively quiet region of space. Perhaps it was this tranquility that allowed life to arise and develop on Earth. Perhaps civilizations like ours simply cannot appear in more active regions of the universe. They are destroyed before they have time to develop. This thought leads us to deeper questions about the nature of the universe and our place in it. Questions that go far beyond physics and astronomy. The existence of giant cosmic structures forces us to think about phenomena of such scale and power that literally go beyond human understanding. We already spoke about the processes occurring inside the Great Walls, but there are events even more extreme. Cosmic catastrophes capable of influencing entire regions of the universe and leaving traces that we observe billions of years later. One of the most striking phenomena of this kind is the collision of galaxy clusters. If the collision of two galaxies is impressive, then the collision of two clusters, each containing hundreds or thousands of galaxies, is an event of a completely different order. These are the most energetic events in the universe after the Big Bang itself. A classic example of such a collision is the object known as the Bullet Cluster, or 1065756, located at a distance of about 3,700,000,000 light-years from Earth. This is a system of two galaxy clusters that passed through each other about 150 million years ago. The smaller cluster, looking like a bullet, pierced the larger one at a speed of about 4,500 kilometers per second. More than 1% of the speed of light. When the two clusters collided, their gas components experienced powerful deceleration. The hot gas of both clusters collided, creating a shock wave with a temperature of more than 100 million degrees. This shock wave is clearly visible on X-ray images as a bright arc separating the gas of one cluster from another. Now, the most interesting thing in the bullet cluster is not the gas itself, but what happened to the dark matter. Unlike gas, dark matter does not interact with anything except gravity. It passed through the collision practically unchanged, carrying the galaxies with it. As a result, dark matter and ordinary matter ended up spatially separated. The mass centers of the clusters, determined by gravitational lensing, do not coincide with the centers of the gas clouds. The bullet cluster became one of the strongest proofs of the existence of dark matter. If dark matter did not exist, and the observed effects were explained by a modification of gravity, we would not see such separation. The mass would follow the visible matter, the gas. No, instead, the mass turned out to be where dark matter should be. The energy released during the bullet cluster collision is about 10 to the 56th power joules. To imagine this number, envision all the energy the sun will release in the 10 billion years of its life and multiply it by a billion billion. That is roughly how much energy is released in one cluster collision. No, the bullet cluster is not unique. Similar collisions occur throughout the universe, especially in dense regions like the Great Walls. Astronomers have discovered many other colliding clusters: Abell, P20, Max J, 0025, El Gordo, and others. Each of them represents a cosmic catastrophe of unimaginable scale. El Gordo, officially designated as SCLJ 024915, is particularly notable. Discovered in 2012, it is located at a distance of about 7 billion light-years and is the most massive known galaxy cluster in the distant universe. Its mass is estimated at 3 quadrillion solar masses. That is 3,000 trillion. El Gordo also represents a system of 2 colliding clusters, and the energy of their collision exceeds even the bullet cluster. Interestingly, the very existence of El Gordo creates problems for the standard cosmology. According to models, a cluster of such mass should not have had time to form by the time we observe it, when the universe was only about 6 billion years old. This is another anomaly that forces scientists to revise their structure formation models. Cluster collisions do not happen instantly. The entire process from first contact to final merger takes billions of years. Throughout this time, the system goes through several stages. First, the clusters approach each other under the action of mutual gravity. Then the first passage occurs when the clusters pass through each other. After that, they move away, slow down, turn around, and approach again. This cycle can repeat several times until the clusters finally merge into a single system. At each stage, colossal energy is released. Shock waves spread through the gas, heating it and accelerating particles to relativistic speeds. These accelerated particles, cosmic rays, can travel through space for millions of years before colliding with anything. Some of them reach Earth, where we register them as ultra-high-energy cosmic radiation. The origin of cosmic rays with the highest energies is one of the greatest mysteries of astrophysics. These particles, usually protons or nuclei of heavier elements, have energies exceeding 10 to the 20th power electron volts. This is about 1,000,000 times more than the energy of particles accelerated in the Large Hadron Collider. One such particle carries energy comparable to the energy of a tennis ball flying at a speed of 100 kilometers per hour, but concentrated in one single atomic nucleus. Galaxy cluster collisions are one of the main candidates for the role of the source of these ultra-energetic particles. Giant shock waves spreading through the intercluster space are capable of accelerating particles to the necessary energies through a process called diffusive shock acceleration. A particle repeatedly crosses the shock front, each time gaining additional energy until it reaches extreme values. In 2017, the Pierre Auger collaboration announced an important discovery. Analyzing the arrival direction of ultra-high-energy cosmic rays, scientists found that they come predominantly not from the plane of our galaxy, but from other directions. This means that the sources of these particles are located outside the Milky Way in distant galaxies and, possibly, in cluster collisions. If ultra-high-energy cosmic rays are indeed born in the Great Walls, this has interesting consequences. The Great Walls are not just clusters of galaxies, but real factories for producing the most energetic particles in the universe. They pump the cosmos with high-energy radiation that spreads for billions of light-years. No, cluster collisions are not the only source of extreme phenomena in the Great Walls. There are processes even more mysterious and frightening. One of them is so-called radio relics. Radio relics are giant arc-like structures radiating in the radio range that are found on the periphery of some galaxy clusters. Their sizes can reach several million light-years. They are larger than the galaxies themselves contained in the cluster. Radio relics represent shock waves frozen at the moment of propagation through the rarefied intercluster gas. The first radio relic was discovered back in 1970 in the Coma cluster. Since then, dozens of similar objects have been found. Some of them strike the imagination with their sizes. The radio relic in cluster Syzhava, 8+531, known as the Sausage Cluster, due to its characteristic elongated shape, stretches for 2 million light-years and is one of the brightest radio sources in the sky in its range. The mechanism of radio relic formation is linked to the acceleration of electrons at the shock front. When electrons are accelerated to relativistic speeds in the presence of a magnetic field, they start to radiate synchrotron radiation, a special type of electromagnetic radiation characteristic of charged particles moving along curved trajectories. It is this synchrotron radiation that we observe as a radio relic. Radio relics are literally frozen snapshots of cosmic catastrophes. They show us how a shock wave looked at the moment of its passage and allow for studying the physics of extreme processes inaccessible for reproduction in Earth laboratories. An even more mysterious phenomenon is so-called radio halos. Unlike radio relics, which are located on the periphery of clusters, radio halos occupy their central regions and have a more diffuse, blurred structure. Their origin is still not fully understood. According to one theory, radio halos arise as a result of turbulence generated by cluster collisions. Turbulent gas movements repeatedly accelerate electrons that previously lost energy, returning their ability to radiate. According to another theory, electrons are born anew as a result of collisions of cosmic rays with protons of the intercluster gas. Whatever the cause, radio halos demonstrate that galaxy clusters are not quiet structures, but turbulent boiling cauldrons in which particle acceleration and energy release processes continuously occur. And in the Great Walls, where clusters are particularly numerous and they often interact with each other, these processes reach maximum intensity. There is another type of cataclysmic events linked to large-scale structures: tidal disruption events. When a star passes too close to a supermassive black hole, gravitational tidal forces can literally tear it apart. One half of the star falls onto the black hole, generating a bright flash of radiation, while the other half is ejected into space. Such events are registered approximately every few months in the observable universe. They give us a unique opportunity to study the behavior of matter near black holes and the properties of the black holes themselves. No, on the scale of Great Walls, tidal disruptions occur constantly. At every moment, thousands of stars across the entire structure are being torn apart by the gravity of supermassive black holes. The energy of a typical tidal disruption is about 10 to the 44th power joules, which is comparable to a supernova. No, unlike a supernova, which lasts weeks, a tidal disruption can continue for months and even years, until all the gas of the destroyed star is gradually absorbed by the black hole. In 2022, one of the most extreme cases of tidal disruption was discovered, event AT 2020. It occurred at a distance of about 8,400,000,000 light-years and was accompanied by a powerful relativistic jet directed almost exactly at Earth. The brightness of the event exceeded typical tidal disruptions 100 times, making it one of the brightest transients ever observed. All these phenomena, cluster collisions, radio relics, tidal disruptions, gamma-ray bursts, occur in the Great Walls with increased frequency simply because of the high density of matter. The Great Walls are regions of maximum activity where the universe demonstrates its destructive power in full. No, there is something else we haven't talked about yet: the long-term fate of the giant structures themselves. What will happen to the Hercules Corona Borealis Great Wall in billions of years? Will it exist forever? The answer is linked to the deepest mystery of modern cosmology: dark energy. We know that the expansion of the universe is accelerating. Galaxies move away from each other faster and faster. The reason for this acceleration is dark energy, the mysterious force acting against gravity. If dark energy continues to act as it does now, in the distant future, the expansion of the universe will overcome gravitational attraction on increasingly larger scales. First, the bonds between superclusters will break, then between clusters inside superclusters, then between galaxies inside groups. In the end, even galaxies and stars might be torn apart by the expanding space. This scenario is called the Big Rip. According to some models, it could occur in 20 to 30 billion years. First, the Great Walls will disappear. Their components will fly in different directions, never to meet again. Then galaxy clusters will break up, then the galaxies themselves. In the end, space itself will expand so fast that it will tear apart atoms and atomic nuclei. No, this is only one of the scenarios. Other models predict that the expansion might slow down or even reverse, leading to the Big Crunch, the opposite of the Big Bang. In this case, all structures of the universe will be compressed back into a singularity. There is a third option: heat death of the universe. Expansion continues but does not accelerate indefinitely. Stars gradually burn out, galaxies cool down, black holes slowly evaporate through Hawking radiation. In an unimaginably long time, 10 to the 100th power years and more, the universe turns into a cold, dark, almost empty space in which nothing will ever happen again. Whatever scenario is realized, giant structures are doomed. They are temporary patterns on the fabric of space-time, destined to dissipate or collapse. The Hercules Corona Borealis Great Wall, for all its monstrous scale, is only a fleeting phenomenon in the history of the cosmos. And this leads us to the deepest questions posed by the existence of giant structures. Questions not about physics, but about meaning. What does the existence of an object 10 billion light-years in size mean for us humans living on a tiny planet by an ordinary star on the outskirts of an unremarkable galaxy? What place do we occupy in a universe of such scales? The first reaction is a feeling of our own insignificance. We are immeasurably small compared to the cosmos. The entire history of humanity is but an instant in cosmic time. All our achievements, all our sufferings, all our dreams are grains of sand in the desert of infinity. In the face of the Hercules Corona Borealis Great Wall, all human ambitions seem ridiculous. No, there is another view. It is we, tiny creatures on a tiny planet, who were able to learn about the existence of these structures. We built telescopes, developed theories, created mathematical models allowing for the understanding of the universe's structure on scales billions of times exceeding the size of our body. The very fact that we are discussing the cosmological principle and its possible violations is a triumph of the human mind. Astronomer Carl Sagan once said that we are a way for the cosmos to know itself. Through us, the universe realizes its own existence. The Hercules Corona Borealis Great Wall existed for billions of years, but it did not know about its existence. Only when intelligent beings appeared, capable of pointing telescopes at the sky and interpreting what they saw, Did the structure acquire meaning? This leads us to an even deeper question. Are we alone? In a structure 10 billion light-years in size containing millions of galaxies and trillions of stars, is there someone else looking at the sky and asking the same questions? The Fermi paradox, the famous contradiction between the high probability of the existence of extraterrestrial civilizations and the absence of any signs of their existence, acquires a new dimension in the context of giant structures. If the universe is so big and so old, if there are so many galaxies and so many stars in it, why do we not see traces of other intelligent beings? Perhaps the answer is linked precisely to those catastrophic processes we discussed: gamma-ray bursts, cluster collisions, radiation flows. All these phenomena can destroy emerging civilizations before they have time to reach a technological level, allowing for leaving their planet or sending a signal into space. The Great Walls might be too dangerous for life, or perhaps civilizations exist, but the distances between them are too great. Even if there is intelligent life in the Hercules Corona Borealis Great Wall, its signals will travel to us for 10 billion years. By the time we receive them, the civilization that sent them might no longer exist, and our own signals will reach these distant worlds when humanity has long disappeared. The cosmos is too big, and time is too long. We might not be alone in the universe, and yet be practically alone in our era and our region of space. Other civilizations might exist in the past or future, might be at the other end of the observable universe. We might never learn about them, and they might never learn about us. There is another hypothesis, more disturbing. What if intelligent life inevitably destroys itself? What if reaching a certain technological level inevitably leads to self-destruction through nuclear war, ecological catastrophe, uncontrolled technologies? In this case, the universe could be full of ruins of dead civilizations that we simply cannot detect. Giant structures in this context become silent witnesses to the tragedy of intelligent life. They exist for billions of years, observing the birth and death of countless stars and planets, and possibly countless civilizations. They are cosmic graveyards of unfulfilled hopes. No, you can look at it differently. The very fact that we exist, that we live to the moment when we can study the cosmos, is a victory. Our civilization survived countless dangers, from asteroids to ice ages, from pandemics to wars. We are still here, and every day that we continue to exist and know the universe is an additional day of victory over the indifferent cosmos. The Hercules Corona Borealis Great Wall does not know about our existence and will never know, but we know about its existence, and this knowledge is our strength. Philosopher Blaise Pascal wrote in the 17th century, "Man is only a reed, the weakest in nature, but he is a thinking reed. There is no need for the whole universe to take up arms to crush him. A vapor, a drop of water is enough to kill him. No, were the universe to crush him, man would yet be more noble than that which slays him, because he knows that he dies and the advantage the universe has over him. Of this, the universe knows nothing." These words were written long before the discovery of galaxies, not to mention great walls, but they remain true. Our consciousness is what distinguishes us from all other matter in the universe. A great wall might be larger than us by an unimaginable amount, but it does not realize itself. We do. And maybe this is the meaning. Maybe the purpose of the existence of intelligent life is the knowledge of the universe, not because it is useful or profitable, but because it is the only way by which the universe can realize itself. We are the eyes and ears of the cosmos, its self-consciousness, which arose after billions of years of blind evolution. Giant structures pose another question for us about chance and regularity. Their existence, if confirmed, points to the fact that the universe is structured differently than we thought. The cosmological principle, assuming uniformity and isotropy, might be incorrect. No, what is correct then? If the universe is non-uniform on the largest scales, this means that some regions of the cosmos are fundamentally different from others. Somewhere there is more matter, somewhere less. Somewhere conditions are favorable for life, somewhere lethally dangerous. We could have ended up precisely in that region where life is possible, simply because in other regions there are no observers. This reasoning is known as the anthropic principle. We observe the universe as it is because only such a universe can contain observers. If physical constants were slightly different, if the distribution of matter were slightly different, we simply would not exist to ask questions. Some scientists are disappointed by the anthropic principle. It seems to them an abandonment of explanation, a surrender before the world's complexity. Others it, on the contrary, inspires. It shows a deep connection between our existence and the properties of the universe. We are not accidental guests in the cosmos. We are its regular product. The Hercules Corona Borealis Great Wall, with all its mysteries, might turn out to be the key to a new understanding of this connection. If structures of such scale exist, they impose limits on the possible laws of physics. Any theory claiming to describe the universe must explain their formation. And in the process of explanation, we inevitably learn something new about the nature of reality. No, there are questions to which science might never answer. Why does anything exist at all rather than nothing? Why are the laws of physics what they are? Why does the universe allow for the existence of intelligent life? These questions lie beyond the empirical method. We can describe the world, but we cannot explain why it exists. In the end, the giant structures of the universe are a mirror in which we see ourselves. Looking at them, we realize our smallness and our uniqueness simultaneously. We understand how fragile our life is and how amazing our ability to understand is. We feel awe before the scales of the cosmos and pride in the achievements of the human mind. Right now, while you are listening to these words, light from the Hercules Corona Borealis Great Wall continues to fly toward Earth. More precisely, it has already arrived. We see this structure. No light from events happening there now will not reach us for another 10 billion years. We are forever cut off from the present of these distant worlds. We can only look into the past, and at the same time something is looking at us. If there is intelligent life in the Great Wall, and if it points its telescopes in our direction, it will see the Milky Way as it was 10 billion years ago. The sun did not yet exist, Earth did not exist, life on Earth did not exist. They will see a young galaxy just forming from gas and dust, not suspecting that in billions of years on a small planet by a small star, beings capable of thinking about them will appear. This makes the head spin. This is a connection across the abyss of time and space. We, hypothetical observers in a distant structure, look at each other but see not each other, but the distant past. The present is inaccessible, only the memory of the universe captured in light. Perhaps this is the message of the giant structures. They teach us humility before the scales of being. They remind us that our time is limited, but our curiosity is limitless. They show that the universe is full of secrets, many of which we will never solve. And they invite us to continue searching, continue asking, continue wondering. The Hercules Corona Borealis Great Wall remains a mystery. We do not know exactly how it formed. We are not sure it even exists as a single structure, and not as a random superposition of smaller structures. We do not understand how to reconcile its existence with our cosmological models, but it is precisely this ignorance that makes it so attractive. Science is not a collection of ready answers. Science is a method for finding answers that inevitably generates new questions. Every discovery expands the boundaries of the known, but expands the boundaries of the unknown even more. The more we learn, the more we understand how little we know. Giant structures are a reminder of how much is yet to be discovered. They are an invitation for future generations of scientists who will build more powerful telescopes, develop more accurate theories, ask questions that we do not yet know how to even formulate. The Hercules Corona Borealis Great Wall will wait for them patiently, indifferently, eternally. And we here and now, on this small planet, can only look at the night sky and wonder. Wonder that we exist. Wonder that the universe is so huge and so strange. Wonder that we are capable of at least partially understanding it. Close your eyes. Imagine space. Imagine how it expands in all directions, filled with galaxies, stars, planets. Imagine the filaments of the cosmic web stretching for billions of light years. Imagine the great walls, giant clusters of matter pulsing with energy and cataclysms. Imagine the voids, bottomless emptinesses where there is almost nothing, only darkness and silence. Now imagine yourself, a tiny point of consciousness in the middle of this infinite ocean, a point that by some miracle is capable of realizing all this majesty, a point that asks questions and searches for answers, a point that refuses to accept its insignificance and continues to strive for understanding. This is us. This is humanity. Small, fragile, temporary, and infinitely curious. The universe is silent. It does not answer our questions. It does not care about our fate. No, we continue to ask. We continue to listen. We continue to look. And sometimes in the silence of the night, when we raise our eyes to the stars, we feel something more than fear of infinity. We feel a connection with the cosmos that gave birth to us and that will absorb us. A connection with everyone who ever looked at the sky and wondered. A connection with those who might be looking at the sky right now, billions of light years from here. We are not alone. Even if we are the only intelligent beings in the universe, we are not alone because we are part of the cosmos. We are made of stardust. The atoms in our body were forged in the cores of ancient stars that exploded billions of years ago. We are children of the universe, and it is our home. The Hercules Corona Borealis Great Wall. 10 billion light years, a structure that should not exist, a riddle that remains unsolved. No, it exists, and we know about it, and this itself is a miracle. Good night.